So we're still exploring the relations between gravitational properties, and we will talk now about the gravitational field relation with the gravitational acceleration. Many of these relations could be not making sense at all at the first glimpse, but when you're moving forward and you set up the numbers and equations together, you'll find out there is a strong relation between these equations. As they say, always the things are not related. If you look at them closer, they are more related than you thought. I'm warning you here, there is a gold that I found in this lecture material, and I'm asking you to go dig into those equations and relations and find your own gold of science. So we know that previously that the force equals the mass multiplied by acceleration, and we know that the force relation with what we defined as the universal gravitational force described by Newton equals the gravitational constant multiplied by m1 by m2 over the distance squared. To find the relation between gravitational field strength with the gravitational acceleration, we need to go back to the basics. The basics are saying in the definitions of Newton, what is the unit of 1 Newton? 1 Newton equals 1 kilogram multiplied by meters over second squared. Where did that come from? That comes from here. Force, which is in Newton, equals the mass, kilogram, by acceleration, which is meter per second squared. Now, we substitute the kilogram meters per second squared for Newton in the equation of gravitational field strength. So we substitute the units of the first law of force in the units for the gravitational force equation. If we do that, we can say, now we start with 1 Newton equals 1 kilogram dot meter per second squared. Now we say, if we divide over kilogram for both sides over here, we can say that 1 Newton over kilogram equals 1 meter per second squared. Now you found a relation between the gravitational field and the acceleration. You can do the same by following this equation equaling to this equation. So ma equals g m1 m2 over d squared. You can have m1 and 2 as a unified mass, and you do the substitutions needed. You will end up with the acceleration would equal the force over the mass. Putting the units together and doing the simplification needed, you will land the unit of 1 meter per second squared. So meter per second squared are the units of acceleration. So in terms of units, gravitational field strength and gravitational acceleration are equivalent. That is really surprising fact, but math doesn't lie. In music, Shakira say, hips don't lie. Here in physics, we say math don't lie. And gravitational field strength equals gravitational acceleration. There is a strong relation here. Now, a table that could be helpful in our next topic. We are still in gravitational acceleration. We have the masses and radii for the bodies in space in our solar system. We have the sun and the mass. Those numbers are actual, coming from Jet Propulsion Laboratory in Caltech. So those are trusted numbers. You can have this table for your reference. And I'm inviting you to go crazy. Take these equations, take these numbers, put them together. Sun and Mercury, Sun and Venus, Earth and the Moon, Mars and Saturn, Uranus and Moon, Uranus and Earth, Neptune and Earth. Do all these things. Try to find the universal gravitational field. Try to find the acceleration between this and that. That is what Newton did back in time, with not very accurate numbers as we have right now, not with the knowledge and online knowledge accessibility we have now. So honestly, your strength and what's in front of you, keyboard, internet, and a PC or a laptop, equals 100 newtons of scientists sitting on your desk. Use those guys, make them tired, and get us some really genuine and nice science that we can use for us and for the next generations. Let's take an example on the gravitational acceleration. Calculate the magnitude of the gravitational acceleration of an object at the equator on the surface of Earth and the Moon, and try to use the previous table. Then next you determine the ratio of Earth, like the gravitational acceleration of Earth, reference to the gravitational acceleration of the Moon. How different would your weight be on Moon versus Earth? We are given mass of Earth, mass of Moon, radius of Earth, radius of Moon. Find the G Earth and G Moon. Then find the ratio, which means dividing G Earth over G Moon and vice versa. Let's try to solve. We use the equation we already know now. Gravitational acceleration equals the gravitational constant by the m source, like the mass of reference you're talking about. Either you're talking about Earth or Moon in this case, over distance squared or the radius of that mass. Now the G Earth would equal G by the mass of Earth over the R of Earth squared. That will give you 9.78 meters per second squared. For the Moon, G by the mass of the Moon over the radius of the Moon squared would give you 1.619 meters per second squared. That is easy. Ratio G Earth to G Moon means G Earth divided by G Moon. That is the definition of ratio. 9.7 over 1.6 will give you 6.04, and ratio is unitless because you eliminate the units altogether. Now let's talk about an object on Mars, how to do the weight calculations for that object. We know that G equal gravitational acceleration equals the gravitational constant by the mass of the source over the center distance to the surface of that source squared, used as well with the another equation of F equal ma, which is for gravitation F equals mg. So you calculate the weight of the object for any space-related body or celestial body, as they call it. I don't like that word. It's just complicating things for no reason. The weight of a student on Mars is calculated. The quantity is compared with student weight on Earth. And many applications are coming in mind for the variations in weight of the objects involved in the Mars rover that we're not going to talk about here. The rover had weighed 2.5 times less than on Earth, so that was, scientists put that in mind and calculate the motion and how much energy and how strong is the motors and the wheels and the structure used for that rover, and inclination of the surface and all those details always being calculated for spaceships and space robots. Now, back to our example. What is the mass of 60 kilogram student on Mars and on Earth? MS, 60 kilograms on Earth. And the mass on Mars, the mass of Mars is 6.4 by 10 to the power 23 kilograms. Mass of Earth, we know it. Radius of Mars, we know it. Radius of Earth, we know it. Find the mass on Mars and on Earth. Now, mass is a scalar quantity and does not depend on location. So, student mass will be the same on Mars and on Earth. But the weight is different. Just keep that in mind. The weight is the force being applied on the body of the student, either on Mars or on Earth. That would be different, or the Fg in this case. But the mass itself is the same. But how strong is that planet pulling the object toward his surface, which is the student in this case? That is differing from planet to another. Now, to find the weight on Mars and on Earth, that is different. So we have the equation G equal the gravitational constant by the mass of the source over the center squared. To calculate the magnitude of the gravitational field on Mars and on Earth, we do the analysis. For Mars, G Mars equals G by m over r squared. We know all these values, plug them in, you get 3.7 newtons per kilograms. And for Earth, the G Earth equals 9.7 newton per kilograms. We are not done yet. We need to find the Fg, which is the m by g on Mars. That would give you the weight of the object on Mars to be 222 newtons. For Earth, the Fg would be mass of the student, same here and here, as you see, mass is not different, but the weight or the force of gravitation is different. Mass of student by the G Earth, which is 9.7, that would give you 587 newtons. So the weight of the student on Mars is less than a half of the weight of the student on Earth. Mass is the same, weight is different. On the moon, on the Mars, usually the weight is less with a certain percentage than the weight on Earth. Now you have the ability to solve problems that are even in the planetary systems. You can solve problems in the space. That's the beauty of science. That's the beauty of physics. That's the beauty of mathematics. You can predict phenomena and scenarios that are coming up in your mind and be accurate about it for something happening on Mars right now, or a black hole in the very far extraterrestrial solar system somewhere in the universe, and you're still able to predict that in a very good accuracy. That is amazing. That's a huge. That is enough to motivate you to learn physics, mathematics, and science.